Hello once again. This time around, we're going to take a look at the law of sines. So previously, we looked at some right triangle trigonometry, basically a different way to define the trig ratios using simply a right triangle instead of the unit circle and the coordinate plane. Um, this time around, we're going to look at the law of sines. Now remember, both of these deal with finding unknown sides and angles of triangles. Both of them or allow us to find these missing measurements and ultimately allow us to model real world quantities and problem solve in the real world, which we did quite a few examples of that in the right triangle trig, and we'll do several more with the law of sines. So let's go ahead and jump to the law of sines. All right, so here we are in our notes. So what if you don't have a right triangle? So every single example we did earlier, you could model the situation with a right triangle. But that's not always going to be possible. Sometimes the situation involves triangles that are non-right. So what do we do in that case? Okay, so let's say we have a non-right triangle. So this is a non-right triangle. And this is its height. It's the height of the non-right triangle right there. Let's call this angle A. Let's call this angle C and this angle B. We'll have this be side C, side A, and side B. Well, using our right triangle definitions, we know that sine of angle A is the opposite leg over the hypotenuse for any right triangle. So if I look at, say I look at this right triangle here, right here, this right triangle, then sine of angle A is opposite over hypotenuse, or H is equal to C times sine of angle A. Grouping symbols for clarity there. And then if I flip it over to this right triangle there, then we know that sine of angle C is equal to H over the hypotenuse A. So H is A times sine of angle C. Now that H and this H are the same. Since they're both equal to H, these two expressions are equal to each other. So C times sine of A is equal to A times sine of C. And then I'm going to divide both sides by C, and then divide both sides by A, and I'm going to get sine of angle A divided by side A is equal to sine of angle C divided by sine C. And this is our important result, is that the sine of any angle divided by its opposite side is equal to sine of the other angle divided by its opposite side. Now what if, now notice that non-right triangle all had angles less than 180. So what if I had, what if my triangle looked like this? So that's a non-right triangle, but it's got this, angle bigger than 90 in it. So this is angle A, this is angle B, this is angle C. This is side A, side B, side C, and then here's the height. There's the height of that triangle. And then this angle in here is 180 minus angle A. That's how big that angle is in there. Well, let's use that right triangle. Let's use that right triangle in there. So with that right triangle with the two red legs, sine of 180 minus A, so sine of that angle would be equal to opposite over hypotenuse. Well, what is sine of 180 minus A? Well, that's a difference formula, so that'd be sine of 180 cosine of A minus cosine of 180 sine of A. Sine of 180 is 0, so that'd be 0 minus cosine of 180 is negative 1. So we end up with sine of A is equal to H over C, which we had earlier. And we showed with that this must be true. So basically, what we're showing here is it doesn't matter what kind of non-right triangle you have. You could have a non-right triangle with all angles less than 90, or you could have a non-right triangle with an angle that's bigger than 90, and you're still going to get this identity, this formula, this little fact. So this is what we call the law of sines. All right, so now we have what is referred to as the law of sines, which simply states that for any triangle, by the way, this does work for right triangles also, it's just not needed because we already know how to handle right triangles. The law of sines simply says that if you've got a triangle with 3 angles and 3 sides, right? There's our 3 sides, there's our 3 angles. The law of sines simply states that the sine of any angle divided by its opposite side is equal to sine of one of the other angles divided by its opposite side. Now, by the way, it doesn't matter which 2 sides or 2 angles you choose. So either one of these would be equal to sine of the other angle C divided by its opposite side. It doesn't matter. Just pick 2 angles and their opposite sides and make a proportion. So you're either going to use these 2, or you would use these 2, or you would just use these 2. Right, you don't need all 3 of them. You just need 2 of them to make a proportion, so you have an equation to solve. And by the way, it doesn't matter if you have an obtuse. So A, B, C. Doesn't matter if it's an obtuse triangle either, this would still work. So this little identity or formula would still hold true. Now notice that this would only work if you knew 2 angles and a side, or if you know 2 sides and one of the angles that is opposite that side. So this won't always work. This is not a perfect formula that works for all situations. Because what if you have a triangle and you know all the sides? What if you know all the sides but you don't know any of the angles? Well, that won't work because you won't have enough stuff to plug into the law of sines. So turns out there's another useful formula and or identity, and it's called the law of cosines. So the law of cosines, let's see where we get it from. So let's say we have the coordinate plane. So this is the coordinate plane. And let's say we put a triangle on the coordinate plane. Let's have this be angle C. Let's have this be angle C. Let's have this be angle A. Let's have this be angle B. So this would be side C. This would be side B. This would be side A. But we're on the coordinate plane. So I actually know what these coordinates are. So if this is length B, then this coordinate right here is B0. And then this coordinate right here would be, well, this angle is C, and it's in standard position on the coordinate plane. Um, so we actually know how to find that. That would be, if we make a right triangle, this would be X, this would be Y, but we can use our trig ratios. So this would be cosine of that angle, and this would be sine of that angle. However, we don't know that we're on the unit circle, right? We don't know, so this would be the radius of the circle, and it has length A. We don't know that that length is 1, we just know that it's length A. So, for example, this distance X, so cosine of the angle is X over R. So X is equal to the radius times cosine of the angle. Well, the radius is A. The radius is A. So this is actually A cosine of the angle C. And then we could show to get Y, right? Sine of that angle C is Y over R, but the radius is A. So Y is A sine of C. So we have to come back up here and adjust because we don't know that this is the unit circle. So this is A times cosine of the angle C, and this is A times sine of the angle C. Now, how is this helpful to us? What is this doing for us? Well, let's go use the distance formula. Let's go use the distance formula between this point and this point to find this distance. We call that distance C. So that distance squared, or I guess if you want to use the distance formula the way we normally write with the big giant radical, so we subtract, so it'd be A minus cosine C minus B squared plus A sine C minus 0 squared. Then we can square both sides. To get rid of the radical. Now let's clean up this by multiplying out those binomials. Let's double check before we square these things out. So it should have been this x coordinate minus that x coordinate. Oop, I snuck in a subtraction that I didn't need there. It should be a cosine minus b, and then it should be that minus 0, that minus 0. Okay, so I think we're okay. So let's square those out. So c squared is equal to a squared cosine squared c minus 2ab cosine c plus b squared plus a squared sine squared c. Okay. Where can I go from there? Well, let's see. What if I move these next to each other and factor out the a squared? And then plus b squared minus 2ab cosine c. Okay. We know that this is equal to 1, so I get a squared plus b squared minus 2ab cosine c. Oh, look at that. So we get this useful formula. So what is this saying to us? That's saying that if you pick any side on a triangle, say you pick this side, but it doesn't matter what side, pick any side, when you square its length, it's equal to the sum of the squares of the other two sides minus double the product of the other two sides times cosine of the angle that's opposite the side that you picked. It's a mouthful, I get it, but useful nonetheless. So this is called the law of cosines. So this is the law of cosines. So the law of cosines says that for any triangle, and by the way, it actually does work for any triangle, not just non-right triangles. But again, we already had a nice, neat little method to deal with right triangles. So this stuff's more useful um, when you have a non-right triangle. But either way, it just says, pick a side. So say I pick this side here, C. So then C squared is equal to, well, here I can color code things, so I'm going to. So then I'm going to have this side be blue. I'm going to have this side be purple. So pick any side. When you square it, it's equal to the sum of the squares of the other two sides minus double their product and cosine of the angle that's opposite this side. So this angle here, C. So these need to be opposite of each other. That's important. Those need to be opposite each other. But again, the naming is arbitrary. So like I could rearrange the letters and get a similar formula for any side that I wanted. So for example, I could have a squared. So pick a side like a and say, okay, a squared. That would simply equal b squared plus c squared. So the other two sides, the sum of the squares of the other two sides minus double their product, so b and c. I'm just following the same pattern, times cosine of the angle opposite the side I picked, which was a. So I mean, the letters are arbitrary. Those are just names I gave to the sides and the angle measurements. What matters is the placement in what the identity said. So this is one of those times where a verbal description might actually make more sense than the symbolic representation of this. But that's up for debate, of course. So what's important here is any side length squared equals the sum of the squares of the other two sides minus double their product and cosine of the angle opposite the side you started with. And that'll give us, that's the law of cosines. Now, look what the law of cosines requires. It requires that you know all three sides, because then you can solve for the angle, or you have to know two sides and the angle that's between them. So if I know angle A, then I have to know the sides on either side of the angle. I have to know the sides that make up that angle, that create the angle. So the way some people remember this is that this is used when all three sides are known. So you could think of that as side, 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 or when two sides and the angle between them is known. So that's side, angle, side. So the way I've always done this is when I see a problem involving triangles that I'm going to model with triangles, I first create the model, right? I draw a picture of the situation. And then I look at it and say, well, is it a right triangle? Then I'm going to use right triangle trig. So opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. If it's not, if it's a non-right triangle, I look at it and say, do I know all three sides? Well, if I do, then I do the law of cosines. Do I know two sides and the angle between them? If I do, I use the law of cosines. But if the right triangle trig and the law of cosines, if neither one of those is applicable, then we use the law of sines. So I always think of the law of sines as a last resort. That's a personal preference, though. No one, you don't have to think of it that way. That's just how I choose to think of my options. Is the law of sines to me is a last resort. Okay, let's give this stuff a whirl. So here's a triangle. We're not going to do a real world problem yet. Let's just do a triangle here. And See if we can get the hang of these new identities, these new formulas. So let's solve this triangle. Let's find all its missing sides and angles. So we have an angle that's 40 degrees. So I'm going to draw a triangle. The triangle doesn't need to be drawn to scale. That's not important. So here's A, here's B, here's C. A is 40 degrees, B is 60 degrees, and the side opposite angle A is 4. So this would be B, and this would be C. It's not meant to be drawn to scale. I just simply put a triangle down so I could label everything. Well, do I know all three sides? No, I do not. Is it a right triangle? Not that I know of. Do I know two sides and the angle between them? So no, I don't even know two sides. So I've got to use the law of sines. Okay, so I'm going to use the law of sines. So the law of sines says that if I do sine of 40 degrees divided by its opposite side, it should equal sine of another angle, in this case 60 degrees, divided by its opposite side, which is B. So if I cross multiply, I get B times sine of 40 degrees is equal to 4 times sine of 60 degrees. So B is whatever 4 times sine of 60 degrees divided by sine of 40 degrees is. And I'm just going to type that in my calculator to get an approximation. And then I'll go ahead and round to the 10th just because I didn't say what to round to. So 5.4 is this now. So this is approximately 5.4. By the way, I can get angle C pretty quickly. Angle C is going to be all 180 degrees in a triangle minus 40 minus 60. So that's what, 100? So this is 80. This is 80 degrees. We know that. So now I just need side C. Well, it's not a right triangle, so I can't do Pythagorean theorem, but I can do law of sines again. So sine of 80 degrees divided by its opposite side, is equal to sine of 40 degrees over 4. And then I can cross multiply to get C. So we can just use the calculator again. So we're going to do 4 times sine of 80 and then divide by sine of 40. And again, I'm just going to round to the 10th spot because I didn't say where to round, so that's what we're going to do. So here's the angle we needed, and here are the two sides that we didn't know. So now we know everything about the measurements of that angle, all angles and all sides. Let's try a real-world application here. Let's see how this works. To measure the height of a mountain, a surveyor takes two sightings of the peak at a distance of 900 meters apart on a direct line to the mountain. Okay, so here's the ground. Here's the peak of the mountain. So here's its height. Height is always a 90 degree to the horizontal. It's height. It's the height of the mountain. And it says that the surveyor takes two sightings 900 meters apart. So sighting number 1 and sighting number 2. So basically they look at the peak, then they moved 900 away, 900 meters, and then they looked at the peak again. The first observation results in an angle of elevation of 47 degrees, and the other one is 35 degrees. Okay. If the transit is 2 meters high, what's the height of the mountain? Okay, we can adjust for the 2 meters later. All right, so we want the height of the mountain. I want H. So why don't we focus on this triangle right here, because we know quite a bit about it. So that red triangle, here's what we know. We know this is 35. We know this is 900. And I can get this one. It's a linear pair with 47 degrees. So it's 133 degrees. And then I could find this side. Let's call that side X. I could do that because I could do the law of sines, right? So sine of 35 degrees over X is equal to, well, something over 900. Oh, I know how to get this. I know two angles of the triangle. I can get that third one. I can just minus them from 180, right? So 180 minus 133 minus 35 tells me that that's 12 degrees. That's 12 degrees. Let's see, that'd be 145. Yep, 180. Look at that. So I can solve that proportion to get x, of course, using the calculator to speed this. I'm going to keep quite a few decimals to maintain some accuracy here. All right, so now I know x. Then I can turn my attention to this right triangle. So now I've got a right triangle here. But now that I think about it, I don't know that side. Oh, I do know I think we're okay. I might be all right. Let's see. So let's write down what we know. This is 47 degrees. This is h. And this is 2482.87526. No, I think we're okay. Opposite hypotenuse. So sine of 47 degrees is equal to opposite over hypotenuse. Can solve that proportion. So the height of this mountain, 1,815.86. But all these measurements were taken with an instrument that was 2 meters tall. So we got to add 2 meters to that. Get 1817.86 meters is the height of that mountain. So I didn't include it in the picture because it just makes the picture more annoying to draw. But basically, the instrument we used to do all these measurements was 2 meters tall. So you have to, all our calculations needed to have 2 meters added to them. We could have included it in the picture. It just makes the picture a little bit more annoying to draw, but it would have worked just fine. Let's try this one. We've got Coast Guard Station Zulu, Station X-ray, a ship at sea sends an SOS call that is received by a station. The bearing of the ship from Zulu, north, bearing from the X-ray is northwest, north to the east, north to the west. Okay. All right, let's see if we can't get this drawn here. So we've got a station Zulu, and it says that when it receives the SOS call, they figure out a bearing to the ship is north 40 degrees east. So here's north, here's east, north 40 degrees east. So we got to go 40. And the ship is going to be somewhere along this line. Okay. That's north 40 degrees to the east. But there was another Coast Guard station called X-ray, and that bearing is north 30 degrees to the west. So here's station X-ray, here's north, here's west, and it's north 30 degrees towards the west. So they're saying that the ship needs to be on this path somewhere. So the ship has to be right here, because this is north 30 degrees to the west from station X-ray. And it says, how far is each station from the ship? So basically, I want to know this distance, which I'm going to call, I don't know, A. And then I need to know this distance, which I'm going to call B. I mean, I got to call them something, so why not A and B? And it says Zulu is due west of X-ray at 120 miles. Okay, so here's what I know. Here's my triangle. This side length is 120. This side length is A. This side length is B. And I know some angles. If this is 40, this must be 50. If this is 30, this must be 60. All right, that's the triangle I have. That's 110, so this must be 70 degrees. Okay, okay. Um, I don't know all three sides, and I don't know side angle sides. This has to be law of sines again, because side, 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 nope. Side angle side, nope. And I don't see a right angle in there. So this is law of sines. So we're going to do sine of 70 over 120, sine of 60 over A. Again, we're going to use the calculator here. Okay, so now we know side A of that triangle. Let's go ahead and do side B. So sine of 70 over 120, sine of 50 over B. Again, we got to solve a proportion, use calculator. And now we know side B. So it turns out that the Coast Guard station X-ray is the big winner. This one's the big winner. That's the one that should send help because it is closer to that ship. So the question is, if a helicopter flying 200 miles an hour is dispatched from the nearest, how long will it take to reach the ship? Well, we know that distance is speed times time. So that implies that 97.82, that's miles, equals 200 miles per hour times time. So that implies that the time, this is in miles, this is miles per hour. So we're going to get, again, use calculator, 97.82 divided by 200. It's going to take about 0.4891 hours. So, 29.346 minutes. Whatever measurement you want to go with. Minutes makes more sense since we're less than 1 hour, but that's fine. I think we all have an idea of about how long 0.4891 hours is, right? Just under a half an hour. All right. Now this time, notice I know two sides and an angle. Let's see what that looks like. So here's my triangle. Again, not drawn to scale. I just need something to label. Side A is 2, side B is 3, and this angle is 60 degrees. So this is side C. So do I know all three sides? No. Do I know two sides and the angle between them? Yes. So this is going to be law of cosines. It's going to be the law of cosines. So the law of cosines says if I pick a side and I know the angle opposite, so this is going to be c squared equals the sum of the squares of the other two sides minus double their product and cosine of the angle opposite the side I started with, which was c. So c squared is actually equal to, again, just use your calculator. This is all just one big calculation, so just carefully type it into the calculator. That ends up being 7. So c is approximately, after you square root both sides, we ignore the negative solution to this equation because you can't have a negative length. We get about 2.65 for side C. So this ends up being 2.65. But I still don't know this angle or this angle. Okay, well, I know law of cosines applies, so I'm going to use it. So doing the law of cosines again, so just make some space here. Let's do angle A. So A is opposite side 2, so it'd be 2 squared equals 3 squared plus 2.65 squared minus 2 times 3 times 2.65 cosine angle A. Again, just be careful, use the calculator. I'm going to subtract these from both sides. So this would be, again, I'm going to use the calculator for this though. Let me get this line out here, it's annoying me. So I'm going to subtract 9. I'm going to subtract 9 from both sides, and I'm going to subtract that from both sides, which is supposed to be what, about 7? So I'm going to get negative 12 equals negative 2 times 3 times 2.65 cosine A. All I did was subtract 9 and that, and 2.65 squared from both sides. Remember, that's the square root of 7, so you're really just subtracting 7. Then I'm going to divide. I'm going to divide by this coefficient here. Again, you can use the calculator. And I'm going to round it, but I'm not going to round it too much because I'm trying to maintain some accuracy here. So cosine of the angle has to be this decimal. So that angle is going to be equal to inverse cosine of that decimal, which, yes, your calculator is going to do for you. Make sure you know what mode you're in. You want to be in degree mode because we have degree measurements here. And after rounding, we get, it's about 41 degrees. 41 degrees for, so basically here's the side we didn't know. Here's the side we didn't know. Here's one of the angles we didn't know. And to get angle B, we don't have to do anything fancy. You just take all the angles in the triangle, subtract from 180. So angle B is going to be 79 degrees, I think. All right, let's do an application question here. So a modeling question. A motorized sailboat leaves Naples, Florida, bound for Key West, 150 miles away. Okay, so if this is Naples, we're going to go to Key West, distance of 150 miles, maintaining a constant speed of 15 miles every hour, but encountering heavy crosswinds and strong currents. The crew finds after 4 hours the sailboat is off course by 20 degrees. Oh, okay. So they get blown off course by 20 degrees. So this is 20 degrees. Now, they didn't find that for 4 hours. They were going 15 miles an hour for 4 hours. So what, 60? That's 60 miles. So 4 times 15, that's 60. How far is the boat from Key West at this time? So now I want to find this distance, x. Okay. Side angle side, right? Side angle side. Yes, sirree. So this is law of cosines. Law of cosines is going to swoop in and help us out here. So this is the side I want to know. This is the angle opposite. So it's going to be x squared is 60 squared plus 150 squared minus 2 times 60 times 150 times cosine of the angle opposite. So x squared is going to be, well, let's see again, you can just type this all in the calculator. 9185.53283. So if I square root that, ignoring the negative, so almost 96 miles away from Key West at that point. So that's not bad, right? They go 60 miles this way, 95 miles that way. You're looking at 155 miles. They only added 5 miles to the trip. It's not terrible. Let's see, what else they ask us? Through what angle should the boat turn to correct its course? Ooh. Okay. So the boat was headed this way, and then the boat's going to have to turn to go on the new path to head to Key West. So I need to know this angle. Interesting. So now I need an exterior angle to this triangle. Again, this requires, you got to kind of think about the boat here, right? The boat's traveling along. Boats don't just stop and turn. Boats, you have to swing the front end, right? You got to swing the front end around. That front end of the boat's got to swing to point it the correct direction. So I need this exterior angle, theta. Well, let's go find this angle, alpha. Let's go find that interior angle. All right, let me make some space here. So 150 squared is equal to 95.841 squared plus 60 squared minus 2 times that side times cosine alpha. Okay, so subtract, and then divide. So it's going to be, I'm going to eventually type this into the calculator, of course. So subtract and then divide. To get cosine alpha. Okay. Let's see what that's going to be. And then, so alpha, you got to do inverse cosine. So inverse cosine of that. And let's see what we get. So we're going to inverse cosine that bad boy. We're going to get 147.64 degrees. That's alpha. We want the exterior angle though. So theta is 180 minus alpha. So that'd be 180 minus what we just got. So that boat is going to have to turn 32.36 degrees. So let's answer the questions here. 95 miles away. It's going to have to turn 32.36 degrees. How much time has been added to the trip? How much time has been added to the trip? Okay. So let's assume that they really can maintain a constant speed of 15 miles an hour. Okay. Let's assume they can do that. So the original trip, they're doing 150 miles at 15 miles an hour. So if I divide, that should just be what, 10, right? So it should have been 10 hours originally. Now they're going to have to go 155.841 at 15 miles an hour. So divided by 15, it's going to take 10.3894 hours. So it's not even adding a half an hour to the trip. It's not bad. 0.3894 times 60. So it's adding 23.364 minutes. That's how much longer it's going to take. So it's not bad. It's not like it ruined their whole day. All right, next up, let's look at why I think that the law of sines should be a last resort. This is called the ambiguous case, is the fancy name that's given to it. And this is kind of the main idea here, that if you absolutely must use the law of sines to find a missing angle, well, then you find yourself in a situation called the ambiguous case. It's kind of a pain. So let me show you why it's kind of a pain. So let's consider the following triangle. Let's say I've got a triangle here. Again, this is not drawn to scale. A, B, C. So side A is 2, side C is 1, angle C is 50 degrees. So I don't know side B, and I don't know 2 of the angles. So it's not a right triangle, so I can't do that. Side, side, side. No, I don't know all 3 sides. Side, angle, side. No. So I can't use the law of cosines. Law of cosines is not an option, which is no good because I like it. Okay. I have to use the law of sines. Well, here's why the law of sines can be a pain and why I don't use it unless I have to. So if I set up the law of sines, it's going to say the sine of 50 degrees divided by 1 is equal to the sine of A degrees, because I don't know A, divided by 2. So now I'm going to be solving an equation for an angle. Solving for an angle. Now we did this earlier, and solving trig equations for an angle is a pain. So I cross multiply, I get 2 times sine of 50 degrees is equal to sine A. So if I get a decimal for that, let me use my calculator. I get sine of angle A has to be 1.5321. Well, that doesn't make any sense because sine, we know that sine has to be between -1 and 1. I mean, we've been dealing with the sine ratio for months now. The sine ratio is never bigger than 1. It's never less than -1. So how can I find an angle where sine of that angle is 1.5? And it's because I can't. I can't. There is no such angle. There's no such angle A. Well, if there is no such angle, then that means this triangle is impossible. So therefore, there is no such triangle with those measurements. So that's frustrating. I was told there was a triangle with a side of 2, a side of 1, and the angle opposite the side of 1 is 50 degrees. But it turns out it's not even possible. You can't even make that triangle. That triangle is not even a real triangle. Quite frustrating, to be kind of going down the path of thinking, oh, I just need to go find these angles and sides, and then all of a sudden find out, nope, that's not even a triangle. You cannot draw that triangle. You can't create that triangle. Let's try this again with some different measurements. So now, here's another triangle. Again, not drawn to scale. So this is angle A, angle B, angle C. Side A is 3, side B is 2, angle A is 40 degrees. So side, 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 no. Side, angle, side, nope. So I got to use the law of sines again. Okay, so sine of 40 degrees over its opposite side is sine of angle B over its opposite side. So I've got to find an angle. I'm solving for an angle again. Dang it. So I'd solve my proportion. Sine of angle B is going to be 2 times sine of 40 degrees divided by 3. So I get out my calculator. Let's see what this is. Okay. Well, at least that's a possible ratio. Sine actually can equal that. So now I'm going to do inverse sine. So B is going to be inverse sine of that. Again, we'll ask the calculator. We get angle B has to be about 25.37 degrees. Okay, great. But wait. We learned earlier that every single time you solve a trig equation, there's an infinite number of answers, assuming there's any answers at all, right? We just saw one up here, but that's not even possible. There are no angles where sine is a ratio bigger than 1. So that wasn't possible. But if there are actually answers, there's actually an angle that works, that means there's an infinite number of angles that works, right? So I want sine to be about 0.4. So if this is the unit circle and positive 1 is up here, 0.4 is like right here. Well, I just found out that that's a 25.37 degree angle. So that's this angle right here. That's the one the calculator gave me. But we know from earlier that there's going to be one on the other side. So there's going to be an angle right here. Ugh. So I need to go find the other angle that has where sine is 0.4285. But I mean, it's not hard to find. It's going to be 180 degrees minus 25.37. So I'm just going to do 180 minus the angle the calculator gave me. And it gives me 154.63 degrees. Okay. But wait, there's an angle that goes all the way around and stops at that same terminal side. So I've got to add 360 to my 25.37 to get another possible answer of 385.37. But wait, I could add 360 to the one I got earlier. But by now, hopefully you realize we're talking about a triangle. A triangle can't have a 300 degree angle in it. So that's not possible. So every other answer I would get to this equation would be an angle that doesn't make any sense for a triangle. So I don't care about any other answers other than 25.37 and 154.63. Those are the two possible angles for angle B. All right, so if angle B is 25.37 degrees, what happens? All right, well, A is 40 degrees, B is 25.37 degrees. Angle C then would be 180 minus those. So angle C is going to be okay. All right, that works. So now I know all three angles. So it's 40, 25.37, 114.63. I know that side A is 3. I know that side B is 2. And side C, I can get that real quick. I can get side C real quick, right? We're using the law of sines, so here we go. We know the law of sines applies, so might as well use it, I guess. So sine of 114.63 over C is sine of 40 over 3. So use our calculator again to solve our proportion. We get 4.24. Okay. All right, so all is right with the world. There's one angle, two angles, three angles, 1, 2, 3 sides. So there's every single angle and side if this is the angle we call B. But remember, there was another option. B could have been 154 some degrees. So if B is 154.63, what would happen? Ugh. Okay. A is 40. That's not up for debate. B, 154.63. So C, if I subtract those from 180, C would have to be negative 14.63 degrees. But you can't have a negative angle inside a triangle. That doesn't work. Because look, angle B and angle A, that's 190 some degrees. That's already more degrees than are available inside a triangle. So this is a dead end. This is not possible. Not possible. So everything we wanted is right here. Everything we wanted is right there. Look how big of a pain this was. So I needed an angle. I could only use the law of sines to find it. And it took me a long time just to figure out the three angles and three sides for this triangle. Let's try one more. Again, here's a triangle not drawn to scale. This is 6, this is 8, and this is 35 degrees. Law of cosines is off the table because I don't know all three sides, and I don't know two sides with the angle between them. So I gotta use the law of sines. Okay. So sine of 35 degrees over 6 has to be sine of angle B over 8. So sine of angle B, using my calculator, is equal to that. That's a ratio that's allowed. That is a ratio that sine can equal. So I'm going to use my calculator. I'm going to do inverse sine of that decimal and see what I get. So I get 49.89 degrees. But again, this is a trig equation where I'm solving for an angle. So there's more than one answer. 49 degrees works. But I would get the same exact y value if I was over here in quadrant 2. So I got to do 180 minus that. That's another possible answer here. So 180 minus that. Another possible answer is 130.11 degrees. Now that's it though. There's no other answers because if I go around the circle again, that angle's too big. Or if I go the negative direction, I get a negative angle. So there's only two possible angles that make any sense for a triangle here, and that's 49.89 and 130.11. So if angle B is 49.89. Then angle A is 35. Angle B is 49.89. Angle C, we just subtract from 180. And now we know all three angles. And those are all angles that can work inside a triangle, so we're good to go. Now let's go get the sides. So side A is 6, side B is 8, side C, well, let's do the law of sines here. Cross multiply, we're going to get side C is about 10.42 units of length. Okay, so we're good. That all of that makes sense for a triangle. Those are plausible angles, and those are sides make sense. Okay, but we had this other angle that we have to consider. So if angle B is 130.11 degrees, well, angle A is 35, angle B is 130.11, angle C, if I take those two angles away from 180, I get 14.89. Well, all three of those are possible angles for a triangle. So it turns out there's more than one triangle that has this side, and this angle opposite of this side. There are two such triangles. Ooh. Well, side A was 6, side B was 8. What's side C going to be? So once again, if I do the law of sines to get side C, calculator's going to give it to me. I get side of 2.69. So there are two triangles. So there are two such triangles. I don't know why I just capitalized that last either, but I did. There are two such triangles. So it says solve the triangle. Joke's on us. There's actually two triangles that have those measurements given. So we have to give both answers here. Which is why the law of sines is always my last resort. I only use it when I have to. And when I have to find an angle with it, well, yeah, not fun. Okay, last thing before we wrap this up is I'll try to give a quick explanation as to why this happens, why sometimes you don't have any such triangle, why sometimes you have one triangle, and why sometimes you actually have two triangles for this ambiguous case. So let's take a look at this diagram here. So if you look closely, you see that we know one side is 6.5, and then we have an angle that's 45, and we have another side that's 6.5. So this is side-side angle, the ambiguous case. Basically, we don't know all three sides, and we don't know two sides and the angle between them. So the question becomes, can you make a triangle out of this? Can you not make a triangle? Can you make one or two triangles? Well, look, if I take this third side to try to make a triangle, I can make a triangle right here. So the moment I put it there, I close it in and get a triangle. So now my bottom side is this, my third side's this, this dashed line down here that stops right there at that X. So boom, I can make a triangle. If I try to put it anywhere else, I can't really make a triangle except for right there. So I can make one triangle out of that. Now, what if I shrink that side? So what if this side was smaller? Now, no matter how hard I try, I can't quite make a triangle, right? It doesn't quite get down to that other side. It never quite encloses a triangle. Or I could make it even shorter to make it more obvious. So I just can't make a triangle out of this. No matter where I place it, I can't form a triangle out of that. Now, there is a particular length in here. There's multiple, I guess. So let's say this side was 5.4 units. Well, now I can make a triangle right there. So that encloses a triangle. But I also could come over here and enclose a second triangle. So there are certain situations where, given how long this side right here is opposite the angle, I can make that triangle or that triangle. I can make two different triangles out of it. Again, just it's meant to be kind of a quick visual as to why sometimes you don't have a triangle, sometimes you have one triangle, and sometimes you have two. By the way, I did not create this visual. This was generously shared on the GeoGebra website, and I'm using it. So I did not create this, by the way.